Okay, I want to just jump right in and start talking about Chapter 1 in the textbook. This chapter really covers an overview of what you've learned in general chemistry. Okay, this is not going to work. Trying some new technology there. Here we go. So it really is a lot of review, and we'll try to reinforce some of the main concepts that you need to know to understand organic chemistry structure and reactivity. Mostly it's a review. We'll talk about atomic and molecular structure, bonding, polarities, how acids and base reacts, and things like that. How we draw structures. These are all important foundations for moving on organic chemistry. And it is a lot of different topics, all sort of summarized in one chapter. So I do want to let you know that although we're going through all these concepts fast, it should be a review for the most part, and we will come back to these and hit them more in depth as we get to them at various aspects of the textbook. For example, we'll talk about double bonds and triple bonds very briefly, but when we get to the alkenes chapter, for example, we'll be going into depth about how the structure of those double bonds are formed and things like that. Okay, so this chapter is titled Structure Determines Properties. And there is nothing more true about organic chemistry than understanding the structures of molecules tells you how they react. Okay, and the structure is actually a pretty complicated thing in a lot of respects, because the definition of the structure is, in chemistry, it's the sequence of connections that defines a molecule. Okay, a molecule, including the spatial orientations, right? But there's a lot more to it. There's different kinds of structure. There's structure at the subatomic level. There's structure at the atomic level. There's structure in how atoms come together, how they interact with each other, how they're connected to each other, different types of bonds and the properties of those bonds. And then there's larger structures. So for example, if you just think about something as simple as a hydrogen molecule, right? That's two hydrogen atoms. Hydrogen bonded to another hydrogen, okay? Two hydrogen atoms. It's a pretty simple structure in that regard. It's just two atoms connected. It's like two balls connected by a string, right? You go to something a little more complicated, like we talked about methane. Methane is CH4, okay? And it has a three-dimensional structure now. It's not all in one plane. It's actually a tetrahedron. And so in order to understand the structure of methane, we have to know a lot about the bonding. So if you take a look at this, it's not all in one two-dimensional space. It's in three-dimensional space. And we have to understand the structure of that. There's larger structure. There's structure in how atoms, which might not be directly connected to each other, pack in a solid form, for example. Or if you have a living system where you have, say, an enzyme, a large protein that has a specific shape in it, where a drug will lock into it, or some other biological function will fit within it, that's also structure at a different level. So understanding structure is very important. In order to understand how organic molecules hold together, we have to understand a little bit about atoms, right? And so hopefully this is nothing new for you. Atoms are made up of protons, neutrons, and electrons, right? So you know a little bit about these properties of these subatomic particles. We know that the mass of protons are about 1.6 times 10 to the minus 27 kilograms. And neutrons are also about the same mass. So protons and neutrons weigh just about the same. They are located in the nucleus of an atom, right? They make up most of the mass of the atom, because we also have electrons present in an atom. But the mass of an electron, if you look at this, the mass of an electron is 4 orders of magnitude less. That's about 10 to the 4th less than a proton or a neutron. So if you think about the overall mass of an atom or an element, the electrons really are insignificant. They're negligible in that overall mass of the atom. All right? So we know we have these particles. Protons, which are positively charged. Neutrons, which are neutral. There's no charge on them. And electrons, which are negatively charged. But how are they structured in an atom? Okay, we talk about structure. Well, we have to think about how they're structured in the atom. If you think about the simplest element, hydrogen, right? An element of hydrogen has what subatomic particles in it? Can anyone tell me?
A proton and an electron.
A proton and an electron, that's right. You have a proton and you have an electron. And we know that those are there, but what is the structure of that? What are the boundaries of that? We know that these aren't just anywhere. That electron is held pretty close to the proton. The proton in this case is what we call the nucleus. But that electron is held in a shell, which we call an orbital, right? So we have to have some idea about what an orbital is. There are no neutrons in hydrogen, so the mass of a hydrogen is? The mass of a hydrogen on atomic units is 1, right? Proton has an atomic unit of 1. The electron mass is pretty much insignificant. Okay, electrons. Now, if you look at the periodic table, of course, we have elements listed there, and there are different descriptors that we have for them. We have the atomic number, which is here in blue, which we call Z. And we have a mass number, which is related to the numbers of protons and neutrons, so the mass number A of the element. And so if you look at a hydrogen atom, for example, it has 1 proton, so the atomic number is 1. Okay, and it's the first element in the periodic table. It has a mass number of 1, because there are no neutrons, and the mass number is the number of protons plus neutrons, which are about equal in mass. Carbon, on the other hand, if you take a look at carbon, right, it has an atomic number of 6. Carbon has an atomic number of 6 protons, but the mass number is 12. Okay, what does that tell you?
6 neutrons.
There are 6 neutrons also, in addition to the 6 protons in carbon. Okay. Now, something else I should point out here: if you take a look at the atomic weight, that is not the mass of that element, okay? The atomic weight is an average mass of a large number of elements, right? Of that element. So, for example, if you take a look at the atomic weight for hydrogen, it's actually 1.0079, not 1. And for carbon, it's 12.0107, not just 12, not a round number 12. Why is it not an integer? Why is it not just a single number? Isotopes, that's right. These are not due to the small amount of electrons. Electrons might vary this last digit a little bit. No, it's due to the presence of isotopes. And so this is an average mass based on different isotopes that are present and their natural abundance. And it's all just the statistical abundance of the various different types of that element. So an isotope, I should ask, what is an isotope?
Same proton number, different neutrons.
That's right. The same proton number, same number of protons. It really is the proton which dictates, the type of element. But there's a different number of neutrons. It doesn't change the overall charge. It changes the mass. So, for example, there's a isotope of hydrogen, which we refer to as deuterium, but it has 1 proton and 1 neutron. And it has a mass of 2. And there's carbon-13. It has 1 more neutron in it than carbon-12. And so those basic things you should really keep in mind as well. Okay, the electrons. We need to talk about the electrons because when we talk about chemistry, chemical reactions, all chemical reactions are really, unless we're talking about nuclear reactions, in which we're mostly not, chemical reactions are a rearrangement of electrons. Electrons are the important things in holding atoms together in bonds. And so when we make bonds and break bonds and do chemical reactions, we are involving the electrons, right? We describe electrons as having properties of both particles and waves, right? It depends on how you're looking at it. And so we know that we can describe the energy of an electron using quantum mechanics and quantum physics. And that was described by Schrodinger. So we have the Schrodinger wave equation. I'm not going to get into quantum mechanics and particle physics here. Just give you a general overview of this. But this wave equation, which is describing the energy of an electron in an atom, we call a wave function. Okay, it's given this Greek symbol psi, and there's a whole lot of mathematics behind that. But what is a wave function? Well, one of the things is we can't really tell exactly where an electron resides around the nucleus at any given time. But we can get an idea about where it's most likely to be. That is, we can calculate the probability. And it is the wave function, actually the square of the wave function, which is related to the probability of where we would find that electron in that atom. Okay, so for a hydrogen atom, for example, you see this sort of blue sphere here. This is the calculated probability of where we might locate that electron if we were to go look for it. And as you go away from the nucleus, the probability of the electron being located there gets less and less as a function of the square. Okay, so the probability in a spherical wave function like this is the electron is probably close to the nucleus. As you get out here to the edge, you see it gets a little diffuse. That's based on the mathematics of the probabilities. And there's a certain point where you have a very little probability of being able to find that electron. Okay, outside that boundary. But that actually, that wave function describes a shape. And that's somewhat interesting as well. Wave functions are orbitals. Okay, you've learned about orbitals, right, in general chemistry. And we have different kinds of orbitals, different shapes of orbitals. Those are simply graphical representations of the quantum mechanical calculations of the probability of finding the electron that resides in that orbital there. Okay, it's as simple as that. We do describe orbitals by their quantum numbers, and so just to remind you and refresh you a little bit about what some of these numbers are, we have 3 quantum numbers that characterize the orbital, and then there's a 4th quantum number that's specific for each electron in the orbital. So we have the principal quantum number, the main quantum number, we have an angular momentum, that's L, and we have a magnetic quantum number, M sub L, and then there's a spin associated with the electron, which could be either +1/2 or -1/2. The principal quantum number, you are familiar with, and maybe you don't remember the connection here. The principal quantum number is related to the energy shell that we're talking about for that element, for that particular orbital. It's an integer, and it is the most important aspect of the energy of that orbital. Okay, so if you think about a nucleus here, and you have an energy shell, so the first energy shell. You can have the second energy shell and third energy shell. And this is all related to how we think about the periodic table. Okay? So in organic chemistry, we deal a lot with s orbitals and p orbitals. So you should know something about the shape and properties of them. What I've been showing so far are s orbitals, which are spherical in shape. So a hydrogen atom has a 1s orbital. 1 being the principal quantum number, s being the type of orbital it is, and this happens to be a spherical orbital. If you go down 1 row on the periodic table, then you have elements which have the second shell, the second energy shell. And so if you look at the s orbital in the second energy shell, it's larger. This happens to be the 2s orbital. Again, spherical in shape. If you go down the periodic table, you have 3s, 4s, 5s, etc. Okay, that's the shape of the orbital is described by that second quantum number, the angular momentum. Okay, L. And this is what in the mathematics we have to use numbers, and so they're assigned numbers. But when we talk about them using the letter descriptors. Right? S, P, D, and F. And so we know now that the s orbital is spherical in shape. Okay, and if you go at any specific energy level, how many s orbitals are there? Like on the first energy level, how many s orbitals are there? One, that's right. Okay, we have p orbitals. P orbitals have a dumbbell shape, right? And at any specific energy level where they appear, from second energy level and on up, how many p orbitals are there? Three, that's right. 3 p orbitals. And d orbitals, there are 5 different d orbitals. They have various shapes. There are 7 different f orbitals, and so on. Now, in organic chemistry, since we're usually talking about mainly the second row of the periodic table, carbon, hydrogen, nitrogen, oxygen, some of the other elements a little bit, we're mostly concerned with the s and p orbitals. Okay, so we should become really, really familiar with s and p orbitals, and then how we hybridize them together. We'll get to that a little later also. Okay, p orbitals are dumbbell shaped, and as I said, there are 3 of them. They are what we refer to as degenerate in energy, that is at any specific energy level, like in this case the second energy level. There are 3 equal energy p orbitals. They are oriented in different planes, right? So we have one oriented in the x direction, one in the y direction, and one in the z direction. Okay? From the second energy level up and higher. And I mentioned that 4th quantum number, the spin quantum number, or m sub s. That's specific for each proton. It can have, electron. It can have either the +1/2 or the -1/2 state. And in an orbital, in any orbital, you know an orbital can hold 2 electrons, right? And according to the Pauli exclusion principle, those electrons must be of opposite spin. That is, if you have an electron that has a +1/2 spin, the other electron in the orbital has to be opposite, or -1/2 spin. No orbital can contain more than 2 electrons. Okay. So with the types of orbitals, those quantum numbers, we can actually describe the configurations of elements. Right? How many people remember their electron configurations? Your general chemistry? It's pretty easy. I've given like the first 3 elements here, and you should be able to do this pretty easily, right? So what's the electron configuration of hydrogen? 1s1. There's only 1 electron in it. So there's only 1 energy level, 1. It's an s orbital with 1 electron. Helium, 1s2, and lithium,
1s2, 2s1.
1s2, 2s1, right? 3 electrons. And so on. And so you should know, right? Remember how to fill out those electron configurations and know what they are. I'm not going to have you filling out a bunch of electron configurations, but you should know them for the main elements we talk about in organic chemistry. You better know them for carbon and hydrogen and nitrogen and oxygen and halogens. Here's the table from your textbook, actually, of those first few numbers of electrons, and as you fill in those orbitals. These are the orbitals here, the 1s orbital, the 2s orbital, 2px, y, and z, and 3s orbital. Okay, those energy shells and orbitals are how we have organized the periodic table. So remember that on the periodic table we have different periods. Periods are the rows, right? And they mean something. The rows and the columns mean something, and the way these are separated out means something, right? So you have the first row with hydrogen and helium, and they have the first energy level shell only. They only have that 1s orbital available. Hydrogen happens to have 1 electron, helium has that orbital filled. The second row has the 2s orbital, and so the 2s orbitals are here on the left, and if you go on the right side, those now start filling in the p orbitals. And the third row, same thing. You have the 3s orbitals here, and you have then, as that's filled, then additional electrons go into the 3p orbitals. I will also say, remember that although the elements in the third row don't have d electrons, it's possible that they could take in electrons into d orbitals and have d orbitals available once you get to the third row. That's why, unlike elements on the second row, carbon, nitrogen, oxygen, etc., these elements can adopt higher oxidation states. So phosphorus, sulfur, you often see oxidation states that are higher than 4. You can have phosphorus 5, sulfur, in higher oxidation states as well. Even chlorine can be higher oxidation states. And remember that the elements that are here all the way on the right side of the periodic table, those are the noble gases, right? The so-called inert elements. And why are they inert? That's right. Their outer shell electrons are full. Right? They're in a very stable electron configuration. So take a look at these. I'm just going to fill this in a little bit. Electron configurations using our spin of the electrons. So, for example, lithium has an atomic number of 3, right? So it has 3 electrons. So as you fill in those orbitals based on the Aufbau principle and Hund's rules and everything you've learned, right? You start filling in these electrons, something like that. You start filling the 1s orbital with opposite spin electrons. The third electron goes into the 2s orbital, right? If you look at, let's just go down to like nitrogen, it has 7, okay? 7 electrons. So we start filling it in, 1, 2. You have the 2s orbital, that's 3, 4. And then the p orbitals, 5, 6, 7. So that's the electron configuration, showing specifically the spins of each of the electrons in the orbitals they're in for nitrogen, right? And then you go all the way down to neon, right? That everything is filled. Every orbital has 2 electrons in it. Okay, it's in a very happy state. It's stable, it's filled, and there's no room to either take out electrons or add electrons. So I've just filled them all in here for you. And I want to remind you also that if you take a look at those orbitals, for these elements like lithium, carbon, nitrogen, oxygen that I've just put here for examples, you notice that you have in the second energy level, the highest energy level of those elements, all the orbitals are not filled, there's spaces. Right? That's where we can have reactions take place. We can fill those spaces or we can take away from those spaces, depending on how full or how empty it is. All right? And this is what leads to bonding, actually, in organic reactions. So let's talk a little bit about ionic bonds. Ionic bonds is one type of bonding, of several types of bonding, and it depends on the formation of ions. Ions are not elements. Elements are neutral. Ions are charged atoms. Now I have to say I made a mistake here. There's a typo on here. I put the electron configuration actually for the row above it. So this, what I've circled sodium here, actually this 1s2, 2s1 is for lithium. So please note that I've made the same mistake with chlorine. 1s2, 2s2, 2p5 is the electron configuration for fluorine, not chlorine. So for chlorine, it'd be one more energy level higher. So chlorine would be 1s2, 2s2, 2p6, 3s2, 3p5. All right, I made that mistake on several slides here, so make sure you note that. So if you take a look at these two, like sodium and chlorine, or lithium and fluorine, if you will, you notice they're on opposite ends of the periodic table. And as the element, they're not in a stable configuration. Right? So what does sodium have to do to become stable, and what does chlorine have to do to become stable? That's the question. So, if you take a look at, again, the numbers are wrong, but the principle's the same. The valence shell, we're looking at the valence electrons. So you have sodium, which has one extra electron in the third 3s1. And you have chlorine, which has one hole in the 3p orbital, right? So what happens is they, of course, transfer an electron. Sodium gives up an electron, it oxidizes, and chlorine accepts an electron. It is reduced, right? And in so doing, you've changed the charges. So now you have a sodium cation, and you have a chlorine anion, right? If you take elemental sodium and elemental chlorine and put them close together, you're going to have a pretty violent reaction, actually. So why does it do this? Well, look at what has happened. Now, there's no electrons in the second shell. I'm sorry, this would be the third shell. So you have the next lower subshell, the shell filled completely. It's in a stable configuration. The same thing, you filled the empty hole that's with the chlorine there, and it's in a stable configuration. Ionic bonds occur when those ions that are formed by oxidation and reduction, electron transfers, come close together. So an ionic bond is a force of attraction between oppositely charged species or ions. Okay, it doesn't have to be just one element ion. It could be a molecular ion. We see ionic bonds all over the place, but they are more common in inorganic compounds. Most of the bonds that we see in organic compounds are covalent bonds. We'll talk about that in a second. One thing I want to point out also is ions, if you dissolve them in solution, they can be separated depending on the solvent. That's not true with things which are bonded covalently. And also, if you look at them in the solid phase, so if you look at sodium chloride or table salt in the solid phase, you see them pack into an organized structure. Okay, structure, there's that word again, right? There is nothing holding this together except the electrostatic attraction between plus and minus. And that can be a strong force. Strong enough to hold the salt together, actually. Okay, ionization. If you take a look at this back at the periodic table, we have looked at things at the very left and the very right of the periodic table. Obviously, if you give up one electron, you become stable, and if you take one electron, you become stable. We see ions forming in the second column too, quite easily, so magnesium in the 2+. It gives up 2 because in order to get this filled all the way to second level, how many electrons would you have to add to it? 7, right? Or for magnesium 6. That's a much harder to do than giving up 1 or 2, and vice versa over here. Okay? Organic chemistry uses carbon mostly as the main backbone, which has a configuration of 1s2, 2s2, 2p2 in the elemental form. So if you were to try to get to a stable state where you have a filled valence shell, the filled outermost energy shell, you would have to gain or lose 4 electrons. Right? And it takes a lot of energy. It's a very high energy state to be a 4+ cation or a 4- ion on one element. So instead of doing that, carbon likes to bond in a different way. It's not easy to ionize carbon to a stable state. And that's where we have a different type of bonding called covalent bonds. Okay, so all these concepts have been known for some time. In 1916, Lewis actually proposed this, that atoms achieve a stable electron configuration by trying to get to filled states. They get maximum stability when they have the same electronic state as those noble gases, right? So again, this is wrong. This should be for lithium. In the lithium cation, which has this electron configuration, 1 and 2, that's the same configuration as helium. All right? Except it's not neutral. That's the only difference. It has a different number of protons in here. Fluoride, if this were right, this would be for fluoride anion, has the same electron configuration as neon. That's the stable configuration. Not quite as stable as those gases because those are actually neutral. These are charged particles. But stable, much more stable than the elements themselves. So we know that atoms want to achieve filled valence shells. And they can do that by either gaining or receiving electrons completely, as in the case with ions, or by sharing electrons. Okay? So when you can share electrons between atoms, they are bonded together in what we call a covalent bond. Okay, a covalent bond. So let's think about the simplest of covalent bonds. That's the hydrogen atom. Two hydrogen atoms. They each have 1 electron. Now, you can certainly see ions of hydrogen, right? We know H+ protons are certainly possible. But if you think about taking 2 hydrogen atoms together, they're the identical same element. So why would one take an electron over the other? There's not much potential for transferring an electron from one to the other. Instead of going to a higher energy state, which would be an H+ H- ionic bond, you would rather just come together and share those 2 electrons between them. Okay? By doing that, they both reached a stable state where they both have filled valence shell. Their 1s orbital is filled because they are overlapping and sharing those 2 electrons among both of the atoms. Okay? That's a stronger bond generally than an ionic bond, and doesn't easily dissociate when you say solvated or anything. Same thing with halogens, so F2, Cl2, Br2. These do the same thing. They have 7 valence electrons. They can easily satisfy and fill that second energy shell by just coming together and sharing 1 pair of electrons between them. Okay? So they have a covalent bond. Each fluorine atom now has the same electron configuration as neon. They have 8 electrons in their valence shell. Okay? This is what gives rise to what we call the Octet Rule. You all remember the Octet Rule, right? When forming compounds, atoms gain or lose or share electrons to give stable configurations characterized by 8 valence electrons. I should point out, I really don't like this, just calling this an Octet Rule, and that just gives you license to memorize Octet Rule in 8. The actual concept of filling the valence shell goes beyond just 8 electrons. When you go to the periodic table, that works great for these second row elements, right? Because you have S and P, you have 4 orbitals total, 1 S and 3 Ps, and the total of 8 electrons that can be accommodated. So Octet Rule makes a lot of sense. But what if you go to something like copper or mercury or gold or molybdenum, right? One of those transition metals. There's a lot more orbitals than just S's and P's, right? There are D's. As a matter of fact, for those to be satisfied and have it all filled, we need 18 electrons. It's the same concept, but if you just memorize Octet Rule, you don't make that connection, right? So learn the concept, not necessarily the pneumatics for remembering things. Okay, carbon. Since we are organic chemists, we're talking about carbon. Carbon has 4 valence electrons. It can form 4 bonds because it wants 8. It's too high energy to give up or take 8 electrons and become an ion. So we can share bonds. So for example, if you take fluorine and bring it close to carbon, you get sharing of 4 fluorines with carbon. So you have 4 points where you're sharing electrons with fluorine. You can do that with other elements as well. Hydrogen. We talked about methane. It's the exact same thing. If you take hydrogen with its 1s electron and bring it close to carbon, it'll share a pair. So then you can put 4 of them around carbon. That fills up carbon. So if you take a look at carbon, 8 electrons around the carbon, right? It's happy. 8 electrons around each of these fluorines, so they're happy as well. Now this is, if you recall, this is what we call a Lewis structure. We've drawn out all of the electrons showing the ones that are shared and the ones that are what we call lone pairs, right? Or unbonded or unpaired unshared electrons. But that gets really tedious to write. Remember what I said at the last class? Organic chemists are lazy. We have shortcuts for everything. One of them is bonds. So we represent a covalent bond more conveniently just by drawing a line between those atoms. So it's important to recognize when you have a line that means you're 2 electrons that are being shared, where one of them came from one of the atoms and one came from the other atom. So originally, if you think about from the original elements, 2 electrons in here, 1 came from carbon, 1 came from fluorine. Okay? CF4. It's the same thing when you have bonds between carbons, bonds between carbon and hydrogen, or any other element. You have a covalent bond, we represent that with a line. When we start to use lines like this, these are referred to as Kekulé structures, and organic chemists also tend not to write all those lone pairs either, unless you're specifically asked to or they're part of describing something. It's important to recognize that as well, because you'll see lots of atoms in molecules that we're going to be talking about this semester that have lone pairs, but we don't explicitly write them all the time. So it's up to you to know what atoms have lone pairs on them and what don't. Okay. So that's how we would write the structure for carbon tetrafluoride, CF4. Okay, atoms, molecules, depending on their valency, that is a number of electrons it takes to fill up those shells, can form any number of different bonds, right? Hydrogen can form 1 bond, fluorine can form 1 bond, carbon can form 4 bonds, and sometimes you can have more than 1 bond between the same atoms. Okay, and we refer to those as double bonds or triple bonds. And we see this all the time in carbons. So here, for example, 2 structures, the Lewis structure and the Kekulé structure. We have carbon dioxide. In order to satisfy its valency with CO2, you need to have more than 2 electrons being shared between those. You need to have 4 electrons being shared between those 2 different oxygens. Okay? This is what we write as a double bond. Okay? Again, we represent it with a line. Each line signifies 2 electrons being shared. Okay? Here's HCN, not nitro, that's HCN. HCN has a configuration where everything is happy. In order for nitrogen to have 8 electrons around it and carbon to have 8 electrons around it, it has to have 1 shared bond with hydrogen and 3 shared bonds with the nitrogen, or 6 total electrons. This is what we have then as a triple bond. Okay? Everyone clear about that? Double bonds between organic molecules, carbons. Now this type of bonding, when we have more than just 1 covalent bond between them, it's actually using different types of orbitals. We're going to get into the specific structure of those later. But on the previous slide you saw that carbon dioxide and HCN I drew in a very linear fashion. It is absolutely straight. They're 180 degrees from one end to the other. Something like ethylene, which is a CH2CH2, connected together by a double bond between the carbons. Actually, this is not a linear molecule, it's a bent molecule. So the hydrogen-carbon-carbon bond is not 180 degrees. Acetylene, on the other hand, which has a triple bond, does have 180 degrees between the hydrogen-carbon bond. So the type of bonding and the number of bonds does dictate, to some extent, structure. Okay? And we'll see that when we get to talking about these functional groups a little more in detail. Okay, any questions on covalent bonds? Definitions of those? Well, the other aspect, which is very important for chemical reactivity, is the nature of those covalent bonds. Not every covalent bond is the same, because we're not always bonding the same element. So we need to consider that different atoms have a different propensity to pull electron density towards it. Okay? This is what we refer to as electronegativity. Because elements of different electronegativity can be bonded with covalent bonds, that means they're not sharing equally the electrons in that bond. That is, if you think about a tug of war between the two elements, the one that's pulling stronger is going to take more of that rope, right? They're going to pull more on those electrons. So the electron density will be closer to that nucleus than the other nucleus. Okay, so it's important to know a little bit about electronegativity and which elements are electronegative and which elements we refer to as electropositive. Okay, and the greater the difference between them, the more polar or polarized the bond. And we have a scale for measuring the electronegativity of various elements called the Pauling electronegativity scale. Here's some of the elements to show you some of these trends. So for example, on the Pauling scale, hydrogen has an electronegativity number of 2.1. Notice that's not a whole lot different than carbon or boron, 2.5 for carbon. All right. But lithium has an electronegativity number of 1. A lot of these alkali metals do. Compare that to the halogens. Fluorine has 4. Chlorine is 3. That's why something like you put lithium and chlorine together, they're going to be ionic. That is, one atom is so much more electronegative that it pulls the electron away and they ionize. That's the difference between covalent bond, where they're sharing, and ionic bonds. The extent of the difference between the two atoms you're talking about interacting. So what trends can you see here?
It's usually more electronegative as you go up and to the right.
It's more electronegative as you go up and to the right, absolutely right. So if you take a look at the periodic table, in general, electronegativity for the elements increases as you go to the right, and increases as you go from bottom to top. Okay? So the most electronegative atom is fluorine. The least electronegative atom, or the most electropositive atom, is francium. And if you took francium and fluorine and mixed them together, you'd have a big explosion. So don't ever do that. It's not fun. So in general, now there are some caveats in this. Other things bonded to the atoms and structure do alter that a little bit, the specific electronegativity. But according to the electronegativity scale, that's the general trend. Okay, and how does that relate then to the bonding? Well, it is very important. So the greater the difference in the electronegativity, the more polar the bond. The more unevenly distributed those electrons are. That's what we're referring to as polarity. A lot of molecules have non-polar bonds. They're not polarized at all. So this occurs when you have the exact same atom, right? You have hydrogen and hydrogen. Same atom, they have exactly the same electronegativity. They're pulling equally on those electrons that are shared between them. So those electrons will be evenly distributed in terms of their probabilities of being there. Chlorine, oxygen. These are diatomic molecules. of the exact same element. This is where it leads to polarized bonds, and then we can have different kinds of reactivity. So we have, for example, if you take HF, very different in electronegativity. Hydrogen has an electronegativity of, anyone remember what we just had on there? On the Pauling scale, 2.1, and fluorine, 4. There's a big difference in electronegativity. This is highly polarized with fluorine holding on to most of those electrons, pulling them close to it. So what happens is this bond creates then a distribution of electrons in the molecule where the fluorine becomes partially negatively charged and the hydrogen is partially positively charged. So you see that listed here. We represent a polarized bond by showing an arrow with a little cross on it. And that arrow is drawn in the direction of the atom, which has the higher electron density. So it kind of looks like a plus sign here, right? If you look at that, that's a plus. So from the positive side to the negative side, that's how the bond is polarized. So if you look at something like water, water is the same thing. H2O, hydrogen is less electronegative than oxygen. And so the bond from hydrogen to oxygen is polarized. Okay? The other bond, right, this is now more than 2 atoms. The other bond is also polarized towards the oxygen. So oxygen here has a high amount of electron density. These hydrogens are much more positively charged. Notice the delta plus, partially positive. It's not a full ion. It's just the way the bond is polarized. Okay, and here you can see the example of carbon dioxide. Since those atoms also are not the same electronegativity, carbon is more electropositive than oxygen. So oxygen gets more electron density in these bonds. Okay, make sense? It's an important concept because when we start to think about reactivity in organic molecules, we are looking for where there is electron density and where there's positive charge density. Okay, that's really critical in thinking about how things react. Using the quantum mechanical calculations, we can actually calculate, based on those electronegativities, the distribution. And so what can be done is you see sometimes things being described with an electrostatic potential map. This is essentially showing that polarity difference and the degree of that polarity in HF with a color map and a size map. So, for example, HF here, the H is largely positive, and you see it's blue colored in this map. That was calculated using quantum mechanical calculations. And the fluorine end is red colored. Okay? Also larger, the atom is larger. The region of negatively charged space is larger. So probably throughout the semester when I'm describing reactivity of molecules, I may pull up some of these electrostatic potential maps to show you how those molecules will react. And finally, this one is not in your book. This is sort of just a generality that I like to share. How do you know what is a polar bond or an ionic bond or a non-polar bond? Well, the thing is that it's a continuum. There's nothing really discrete between what is a covalent bond. Well, if it's completely separated, then it would have to be ionic or not interacting. But in general, there's a rule of thumb that if the difference in the electronegativity on that Pauling scale is less than 2, then you're sharing electrons in their covalent bonds. If it's greater than 2, that's generally then separated ions in their ionic bonds. The electron is actually transferred over from one atom to another. But in between are a whole lot of other areas. So this is a continuum, and you can find examples of molecules at every place along that continuum. Okay, so it's important to understand sort of the degree of polarity when you think about reactivity. Okay, Monday is a holiday, so have a good weekend, and we'll see you back here on Wednesday. I will try to get an assignment, a test assignment put up on the online homework system by Monday if I can. So even if you're not here, you can log on and check it. See what's happening. Okay?